So in this video, I'll be covering equation of a line in two dimensions. Now we need to understand the reason why we are interested in equations of straight lines when studying linear algebra. Okay, it's with a very specific purpose. We'll come to that. Now, almost invariably, and at least when I was in school, the most taught format of the equation of a straight line was y is equal to mx plus c. Okay, where x and y are of course the x and y coordinates of points on the line, m is the slope of the line and c is the y-intercept. Now there was a good reason why they taught us lines in school in this format, because this format lends itself very easily to visualizing how the line will look. So if this is your xy plane, once you were taught your concepts, you knew m was the slope, and it was known, we knew that if m is positive, then the line kind of starts high on the right side and slopes downwards as it goes left. Okay, so this was the case of positive slope or positive m. If m was negative, then we knew that the line started high on the left side and sloped downwards as it went right. So this was about how the line tilted, right? There are special cases of vertical lines and horizontal lines. I'll come to that in a moment. But m was all about the tilt of the line. Okay. Now, after knowing the tilt, or at least which way it tilts, C told you exactly where the line would cut the y-axis. Okay. So if C was positive, then the line would cut the y-axis above the origin at the value that C had, here for example. So then, combining the slope m and the y-intercept, you had your line. This was for negative m's, something like this for positive m's. Okay. Now just the value of m would not tell you how much to tilt the line. You could go into trigonometry, where m was really tangent of the theta with the horizontal, but let's not get into those complications. But given this format and given actual values, for example, if they told you y is equal to 2x plus 3, you could visualize how the line was going to play out in the coordinate planes. To actually nail the line down, of course, all you needed was 2 points. So if you had something like y is equal to 2x plus 3, you might try, x equal to 0, then figure out that y was equal to 3, and you could try y is equal to 0, and then figure out that x was equal to minus 3 by 2. And then you would get your 2 points, this one here, and this one 1, 2, 3 here, and you had your line. So that was the worth of y is equal to mx plus c. Of course, so why are we learning y is equal to mx plus c here? It's not really that useful in linear algebra. I think we are doing it just as a tribute to the equation of the line and to get into the groove of things. There are of course special cases. You could have an equation where x just did not appear. So you could have y is equal to c or y is equal to 3. Another form of that equation could be y is equal to minus 5. So c positive, c negative. Now if x was missing from the equation of the line, either this or this, what it really meant was x could take any real value. Okay. We keep on reminding ourselves that x, y are elements of the set of real numbers. Now, what does it really mean to say that x can take any value, right? Y was equal to 3 and y would always stay 3 and x would take any value. That meant a horizontal line 3 units above the origin if c was positive, which it is here, and if you had this case 1, 2, 3, 4, 5, then you had a horizontal line. Okay. The other special case was if y was missing, okay, then the line would end up taking, if you were to translate this equation, then you would have something like x is equal to minus c by m, but really that means x is equal to some constant a. Y is missing, which means y can be anything. So, it's really saying x plus 0y is equal to a. No matter what value of y you put in here, the 0 will zero out this expression and you are going to have x is equal to a. That's what it really means. Likewise, y equal to 3 really means y is equal to 0x plus 3. Okay. So in this case, you are really talking of either a vertical line this way. If a is positive, then you are to the right of the origin. This is the origin. And if a is negative, then you are to the left of the origin by a. So this distance would be the absolute value of a. So would this distance be the absolute value of a? Of course, the point here would be a0 and the point here would be a0. A would be negative here, a would be positive here. So that's about y is equal to mx plus c. We just did it, we actually did it just to, as a backgrounder, get back to our school days and set the stage for further discussions around the equation of line. Okay. Now, I could restructure this equation. I could just take y on the same side of x and I would come up with mx minus y plus c is equal to 0. Now this actually is called the standard form. I think this is called the standard form. Y is equal to mx plus c, I guess, is the slope intercept form, and there is a third form which is the point slope form, I think. So, you use this ideally if you know the slope and the y-intercept. You use point slope form if you know one point on the line and the slope. Okay, I won't go into how we construct a line, but just to quickly do it, that would be y minus 5 upon x minus 1 is equal to 5. That would give you the equation. So these are the three forms. I'm just going to leave these two. This one because it was our favorite and the one that we were most familiar with in school. Now the standard form, instead of writing it as a converted form of the slope intercept form, is ax plus by plus c equal to 0. Now I am going to remove the slope intercept form because, let me leave it there. We are done with it actually. Okay. Now, for the reason that I will explain later, this is the form that really is a brilliant tool to use in linear algebra. And since that is the case, even though in linear algebra the name of the game is not to draw the line itself, I think we owe it to ourselves to try and figure out, how these values would shape the line. Okay. And there is no good way to immediately discern it based on things like this. But I'm going to just think in my mind, and I guess in my mind I'll be trying to put this equation in this form and try to figure out what will happen. Okay. So I say that if a, b are both greater than 0, if a, b are both greater than 0, or if a, b are both less than 0, In that case, I am going to have a line sloping, starting high on the left and sloping downwards on the right. If one of A, B is positive and the other is negative, then it is going to slope the other way. Like the m is equal to m is positive way, right? It starts high on the right, slopes downwards towards the left. That leaves us with C, right? Or rather the y-intercept. And I say this is going to be the opposite of what we have here. If C is positive, then my intercept is going to be downward from the origin. And if C is negative, my intercept is going to be upwards from the origin. Either this way or this way. So, if A, B are both greater than 0, I get a line like this. If one of them is positive and one of them is negative, I get a line like this. Okay. If C is greater than 0, if C is greater than 0, then I am going to have a negative y-intercept. And if C is less than 0, I am going to have a positive y-intercept. Okay. So that gives us an idea of how ABC, as we know, I hope we know, are coefficients of the variables. Okay. Yes, coefficients of the variables x, y. So that really means A, B are the coefficients and C is a constant. Coefficients of these variables and C is the constant. And these three together decide how the line will be shaped. The one case that we missed in both cases is lines that pass through the origin. Okay, and in both cases it's quite simple. If C is equal to 0 in either case, the line is going to pass through the origin. Which way it slopes or whether it's vertical, horizontal is decided by what we discussed earlier. The vertical horizontal is this way or this way is decided by the signs of these coefficients, and the vertical horizontal is defined by respectively. The vertical is defined by the absence of y and the horizontal by the absence of x. So I think that's, again, I wanted to do this for familiarity. I am not entirely sure that in all your forays into linear algebra, you will come to a point where you might want to guess or quickly know the way the line is shaped, but you just might, and if you do, why not have the familiarity? Now, why did we learn this in school? Because from the point of view of understanding how the line will look, how it will slope, where it will hit the y-axis and the general positioning, this form is the best suited. And since in school, our objective behind using equation of a straight line was to really study the geometry of lines. This was most suitable. We are done with that. Okay. Now, why is this important in linear algebra? Okay, let's come to that. And to do that, to understand that, I may use some terms which we have not gone through, but I think vectors we have spent a great deal of time, so you should be comfortable with that. And the two reasons or the two contexts in which this form of the equation keeps on coming up. Okay, the first context is linear combinations, which we have studied. And linear transformations, which we have not studied, but we can talk about them and then again bring them up or bring up this equation. It will anyways come up when we do linear transformations. Linear combinations. Okay, so what are linear combinations? Linear combinations are additions of scaled multiples of vectors, right? So I'll quickly write an example. If you are just in 2D, you have these two vectors, say 3, 0. It is an addition of scaled multiples. So I'm going to scale this guy with some scalar, and I'm going to scale this guy with some scalar. Okay, and this goes on to become a vector, correct? Okay, so quickly, 3 plus 21, 24, I don't really need to do this, but 6 plus 0, that is 6. So that's a linear combination. Okay, and we know that given two vectors, we can have multiple linear combinations, correct? So I am going to do something here. Whatever it comes up to, correct? So let's say this is a vector. Since we don't know x, y, we don't know this. Now if I multiply this out, I get x and 2x plus 3y. For the right reason, I am going to replace this 0 so that we see the equation in all its glory. We have studied, we have not studied, we have studied vector addition, that's fine. I was about to say we have not studied matrix addition, but we have studied vector addition. That quickly, I think it gives you an early idea of how vectors and matrices intermingle, but more on that later. What this really means is, and that really means x plus 3y is equal to C1, 2x plus 5y is equal to C2. If you look at the format of these equations, this is more in line with this than y is equal to mx plus c, correct? And suddenly you go back to school geometry in a way, because now what we are seeing is, given these two vectors and the vector you want them to combine to, let's say this is 7, 9, right? I now put actual numbers, 7, 9, 7, 9, 7, 9. Then the problem of finding that linear combination of these two vectors which results in this vector, that is finding the correct scalar multiples, suddenly becomes a problem of solving a system of linear equations, correct? And now look at it this way, the problem really is to find the scalar multiples, that is the correct linear combination, but it also becomes a geometry problem, because these are two straight lines, and wherever they intersect, that point, those values of xy, okay, we are in the coordinate plane now, so those values of xy are going to be our scalar multiples. Now again, there is no deep or profound connection between intersection of lines and linear combinations of vectors. It is just that two branches of mathematics or two sub-branches of mathematics or two topics of mathematics beautifully converge, so that the techniques in the matter of solving these equations can be applied to linear combinations. Okay, and that is why we spend some time understanding this format of the equation, because really you are going to be solving that. Now, geometry will help you interpret things, especially when you go to 3D, right? There the equation of a line, equation of a plane, etc. will be extremely important, and it will give you just an added validation to the conclusions that you will reach about linear combinations, which actually further extend into the topic of linear dependence and independence. Okay, so if I were to very formally say something, then in linear algebra, when vectors are stacked up to form a linear combination, when vectors are stacked up to form linear combinations, the values within the vectors, right, the numbers within this ordered list or these two tuples end up becoming the coefficients of variables in the system of linear equation, and the scalar multiples end up being the variables in the system of linear equations that you end up with as a problem to be solved to solve the problem of linear combination. Okay, very important. Coming to this side of linear transformations, and we have not really done matrices, but I will tell you, this linear combination can also be written as 1, 2, 3, 5. Now here we are talking of a matrix. Obviously this is not a vector because it has more than one columns. We will cover this when we come to linear transformations, but think of this as a function. Okay, given any vector, if you multiply that vector to this matrix, and let me tell you that by the rules of matrix multiplication, which you probably know, this is a valid matrix multiplication because the number of columns here match the number of rows here, and as we know, the resultant vector has these many rows and these many columns. Okay, so think of a linear transformation as a function which transforms any vector, any two tuple vector to 7, 9. Yeah, I think that is the way to look at it. Okay, so several points going to 7, 9. I never realized that, but that's what it means. And actually that's not the correct way of looking at it. There may be multiple values, there may be a single value, but what this is saying is this transformation represented by the matrix transforms a certain vector into the vector 7, 9. So what is the vector? What is the source vector? Okay, and once we do matrix multiplication, you will immediately know that here we are really talking again of x plus 3y, 2y plus 2x plus 5y is equal to 7, 9, which you will quickly realize goes on to become this problem. So I think we have demonstrated to ourselves abundantly why this standard form of the equation of a straight line is important and where it comes up. So the confusing part, which once you get used to it, it becomes kind of second nature to you. A geometric interpretation a system of linear equations, linear combinations, linear transformations, and something that we touched upon earlier, linear dependence / independence. We are getting an early view of how all of these link up together. Now, the last thing I want to quickly talk about is, we are still talking of 2D, but the same concepts will go on and extend into n dimensions. Okay, so when you go into n dimensions, instead of now relying on distinct alphabets, because there's only 26, we are going to start using alphabets with subscripts. So I'll quickly write it. Plus, maybe I'll just write the C as it is. This becomes an equation of something in n dimensions. And though we will cover this later, I am going to give you an early piece of information. In n dimensions, this equation in n variables represents something called as a hyperplane, which is a n minus 1 dimensional object. I am not going to go into any further explanations here, but please remember that.